So the previous video talked about what an event is and how to write a probability as a fraction, and this video is going to complete the first section of probability and start to talk about how to create a sample space. So a simple event I mentioned in the last video would be, in this case, like a single birth. And so a girl would be a simple event, but also having a boy would also be a simple event. So that sample space is two events, and that is your sample space. So the probability of having a girl would be 1 out of 2. Probability of having a boy, right? Probability boy would be 1 out of 2, because there's 1 out of 2 possibilities. Now, 3 births, they started showing you this sample space, BBB, BBG. So the first child's a boy, second child's a boy, third child's a boy. First child's a boy, second child's a boy, third child's a girl, right? And they start showing you all of these different possibilities. So now these 3 simple events create one of the events in the sample space, because one event would be 3 births instead of just a single birth. So 3 births, the event 2 girls and a boy, is not a simple event because it can occur with different possibilities. So if you have 3 births, we can't call this a simple event because there's more than one possibility. BBB is different than BBG. So a simple event is just something where it's broken down and it can't be broken down any further. Don't stress too much about the difference between a simple event and a compound event. In this slide, mainly I wanted to show you the idea of a sample space and how that sample space is going to help us come up with the denominator of our fraction when we start coming up with probabilities that are related to this situation. So a tree diagram is often what's used to come up with the sample space. And if I'm trying to come up with the sample space of having 3 children, it would be like each branch would represent each child. So for example, you've got the first child, you've got the second child, you've got the third child, and so this tree is going to branch out like that. Okay, so if I wanted to show the 2 possibilities for the first child, I could put a B and then a G. And then if I wanted to show that this family had another child, what I could do is put those same 2 branches, B and G, off of the first event was that they had a boy. But then the chance that they will have a boy or a girl on the second child remains the same. And so this represents 4 different possibilities. They have a boy, a boy, a boy, a girl, a boy, and then a girl and a girl. And then so you can hopefully see what's happening with the third child. You know, every time they have a child, the probability of having a boy or a girl does not change. And so what you can do is create your sample space this way. It's kind of a way to organize. If we were studying probability for weeks and weeks and weeks, you might start figuring out how you're going to organize your list. But if this makes sense to you, the way that I'm sectioning off these branches, these are the 8 possibilities, the 8 possible things that can happen if a family chooses to have 3 children. So there's 1, 2, 3, 4, 5, 6, 7, 8. I'll talk a little bit about the next section, which is the probability of compound events, and what are the possible things that can happen. And really there are 8 possible things, right? 8 total possibilities. And what you could have done, What we could have also done is figured, well, there's two possible things that can happen after the first child, and then there's two things that could possibly happen after the second child, and so the possibilities doubled, right? For each of the two original possibilities, two more possibilities kind of branched off. And then there were two more possibilities. And so 2 times 2 times 2 would have given us this total of 8 in our total sample space. So basically, figuring out what the total possibilities are will help you, because if the probability question starts with, if a couple has 3 children, if a couple has 3 children, and we are writing fractions to represent our probabilities, 8 would be the denominator. Those are the total possibilities. And then the numerator would be the probability of having 2 boys, if I was answering that question. And in this case, it's more specific, a girl and then 2 boys. So that would be the G, the B, and then the B. And so if you have your tree diagram written, we could count how many of the branches satisfied whatever probability they're asking. So let's go back and answer what's the probability that they will have 2 boys. So that's not saying exactly 2 boys, and that's where things can get really tricky, annoying, and specific. So if they have 3 children, what's the probability that they have at least 2 boys or exactly 2 boys? I should have qualified that a little bit better. So I'll do that right now, and we'll say that the question is at least 2 boys. So that's why maybe having the list might be better than the tree diagram. You know, if you are able to create that list yourself, like, well, they can have a boy, and then they can have a boy, and then they can have a boy, or they could have a boy and then a boy, and then they can have a girl, or they could have a boy and then a girl and then a boy, and then they could have a boy and then a girl and then a boy. So I went through like the 4 different things in my head that could occur if they started with a boy first. They could have a boy and then a boy, or they can have a boy and then a girl. And then I can think of the different ways that they could start, have a child starting with, what if they had a girl to start with? Well, they can have a girl and then a girl and then a girl, or they can have a girl and then a girl and then a boy, or they can have a girl and then a boy and then a girl, or they can have a girl and then a boy and then a boy, right? So, again, if you do probability a lot, you might be able to come up with this list systematically in your mind. The tree diagram is just another way for you to not have to think so hard. Even as I'm writing this, I'm wondering if I made any mistakes, but I think I nailed it. And I can go back to the tree just to double check. So at least 2 boys. This family has at least 2 boys. This family has at least 2 boys. All 4 of these have at least 2 boys. This has only a single boy. So of the girl side, if they had a girl first, there would only be one possibility that they had 2 boys. So that's a grand total of 1, 2, 3, 4, 5. And then you can change that into a decimal. 5 divided by 8, I'm typing over here in my calculator, is 0.625 probability. The second question is, what if they started with a girl and then had 2 boys, and that would only be one of the 8 possibilities. Change that into a decimal and you get 0.125. So those are a little bit more tricky probability questions, because you have to come up with the sample space in order to be able to identify, both the numerator and the denominator. The denominator tells you have to figure out what the total is, and then you have to go and pick out the ones that satisfy. So earlier you saw this notation. Complementary events would be if they put P representing parentheses, and then they put something like the letter B with a line over it, and that's the probability that something does not occur. So this example is related to another survey by the Pew Research Center that 1,782 people were surveyed, and they say that they do use the internet, and 2,002 people were surveyed, so that's your total, and then 1782 said that they use the internet. So A represents they do use the internet, so that yes. And then this probability would represent the probability that A doesn't occur, so they don't use the internet. So the first probability, I would use the 1782 because I am trying to figure out the probability that they do use the internet. I would divide it by 2002. And then to calculate the other probability, what I would have to do is take the 2002 total people that responded and subtract the number of people that said yes, and that would give me the total of people that said no. And so the textbook has calculated that for us. Again, this 220 that they're using to represent P not using the internet would be the numerator. Again, that came from the 2002 total people minus the 1782 that said that they do use the internet. If you took notes on this slide, that's this probability. The probability that they don't use the internet is just going to be 1 minus the probability that they do use the internet. So the last part of this lesson is just, when people talk about probability, they're either using the classical approach, is what we just did. They're using their experience, or they're using their experience but with some data behind it. And so the classical approach is what you've seen, is that we just take the total number of ways that something occurs divided by the total in the sample space. And this is only true if everything's equally likely to occur. And so that's the type of examples that we were doing with what's the probability that you're going to have a girl versus a boy. There's an equal chance of that. Subjective probability is personal experience. So you'd be like, oh man, I'm probably going to ace this test because I always do. That's, not the kind of probability that we will be using in this class. And so what's the probability you're going to earn an A in this statistics course? Well, it kind of depends on all kinds of things, but depending on what your experience is, you might give a probability to what you think what's going to happen to you based off of your own experience. Relative frequency is a probability that happens based off of experience, not on something having an equal chance of occurring. So, for example, when trying to determine the probability that somebody's going to get a car accident, they think about all the times that they've been driving, and they try to calculate some kind of probability. Now, that's not exactly mathematically sound, but it's more like the kind of probability that happens, and what we try to do in statistics to try to predict what could possibly happen. And so we'll end with this last side, the law of large numbers, that says that if a procedure is repeated over and over again, that the relative frequency probability tends to what the actual probability is. So if you run an experiment enough times, that you're going to get close to what the actual true probability is of something actually happening. So that, again, we're still living in the land of probability. We've got 3 sections, and hopefully this is a good outline to help you get through that homework.